Now, welcome back. Boy, we've had quite an adventure the last couple of weeks here in class. We now understand better why the periodic chart is the periodic chart, why it has the shape and the really deep knowledge that is built into the periodic chart. We understand better why families have very similar chemical and physical properties. We understand why they form the charges that they form. Today, we're going to talk about compounds. We're going to go back and revisit ionic compounds. We're going to talk a little bit about covalent compounds and how to tell what kind of compound you're going to have. There we go. We're going to talk about a very important concept called electronegativity. And we're going to go back and revisit nomenclature a little bit. This is kind of a I'm not even sure what that silver. Oh, I don't think I quite finished silver. I was doing silver as the example of how you can just read the electronic configuration off of the periodic chart. We never finished it. That's why it looks so odd to me. So it'll be a good review. Let's do that. So silver is all the way down here. I actually switch to a pen. So to read silver, as you recall, go up one period and over to the noble gas. That krypton there, is that krypton? That's krypton. That represents the inner shell electronic configuration for silver. So we put krypton in the square brackets. But notice that silver is in the 5th period. We are past the S block. So we have 2 electrons in the S. Remember to drop down 1 period for the transition metals. Remember to drop down 2 periods for the lanthanides. Then just count how many electrons are in the D. It's 5s2, 1, 2, 3, 4, 5, 6, 7, 8, 9, D, 4d9. 4d9. So it's 5s2, 4d9. And this is actually kind of an interesting start. It's a nice segue into what we're going to talk about today, because we've talked about the charges of some of the elements. The first row, the alkaline metals, are all +1, and we understand now why it's all +1, because they all have that 1s electron. They're trying to get rid of that 1s electron to give them the noble gas electronic configuration. That's all they have to do, is just lose 1 electron. They're all +1. The alkali earth metals are all +2 because they have 2 electrons they need to lose. Silver, this is the inner shell electron. The nearest noble gas is, well, actually probably not krypton, but xenon. But it either has to lose 11 electrons or gain 7 electrons. And that's a lot of electrons to lose or to gain. So silver will not the charge of silver will be, it's not going to be able to do it because the charge density, that is to say, if it loses or gains so many electrons, it's going to have such a high charge density, it's just not going to be stable. So it can't do it. Sometimes when you look at the electronic configuration of these elements, which we can represent graphically like this. There are 5d orbitals. So we put 5 dashes down. There's one s orbital, so we put 1 dash down. There are 4 p orbitals. If silver actually used its p block electrons, we would put down 5 more dashes. This may or may not look familiar to you. This is just a graphical representation of this electronic configuration. Sometimes books will use circles. Sometimes they will use squares. I've always used dashes. Notice there's a little space between the 5s dash and the 4d dash, just to sort of represent the different shells so we don't get them confused. As you begin filling these, if you want to do this kind of graphical representation, remember 2 electrons can fit in each orbital. Each one of those dashes represents one of the orbitals. But remember, orbitals can hold 2 electrons provided they are opposite spin. So we have 2 s electrons, which I'm going to represent as a spin up and a spin down. And we have 9 d orbitals. Now the question is, do you start pairing them up, or do you go 1 per orbital first? Well, remember, electrons are negatively charged, and these orbitals represent a small region of space. So there is electrostatic repulsion. Even if they're opposite spin, there's still that electrostatic repulsion. So always begin filling 1 electron per orbital and then begin pairing them when you run out of orbitals. So there are 9d electrons. So 1, 2, 3, 4, 5. Now each orbital has 1 electron. We have no choice but to go back and repair. By convention, and these are just conventions. Remember, this, what we're talking about today are cartoon representations of electrons. They're just cartoons. By convention, you always begin with spin up and you always go from left to right. It doesn't mean anything. It's just spin up and left to right. And I have a chat here. What's my chat? Oh, that's fine. Thank you very much for letting me know. Now that they're paired, no, I'm sorry, now that we have 1 in each orbital, now we go back and repair. Five, 6, 7, 8, 9. Now we have 9 electrons. So this is the electronic configuration for silver. And it looks a little odd. It has that 1 unpaired electron, which makes it a free radical. Anytime you have an unpaired electron, it's called a free radical. It is highly unstable, very reactive. It's very unhappy. When you start looking at the electronic configurations, and I'm just touching on it today, we probably will not revisit this later, but when we are looking at the electronic configurations of those transition metals, sometimes you can understand what it's doing in order to stabilize itself. Like I say, it's not going to be able to lose all 9d orbital electrons. It's stuck. It's, what can it do? As it turns out, the most common oxidized state for silver, the most common charge, is +1. And if you look at the electronic configuration, sometimes you can figure out the compromise it's trying to make. And here you can see quite clearly what it's trying to do. It has one unpaired electron. So the silver +1 charge is just getting rid of that unstable unpaired electron. And even though we don't normally fill orbitals this way, that means it will have an empty d orbital. There are ways to prove if this is indeed what it's trying to do, but those transition metals in the middle, sometimes they'll have multiple charges possible. Iron tends to be either +2 or +3, for example. And we're going to talk a little bit about that in nomenclature. But today we're going to talk about the Pauling electronegativity scale. Whatever book you're using, and remember I told you you can use any book you want, there's probably a chart in it that looks like this. This is the Pauling electronegativity scale. And we're going to use this periodic chart today. So if you want, you can find your Pauling electronegativity chart and turn to that. In my book, it's on page 82. But I wanted to start by looking at something called Lewis dot structures. Lewis dot structures are designed to help us understand bonding. If you recall the octet rule, where does the octet rule come from? Well, if you look at, for example, argon. Argon has neon's electronic configuration for its inner shell electrons. And it has two, again, you can just read this right off the periodic chart. It's the third period. So it's past hydrogen, it is past the alkaline metals and alkali earth metals. So it has two s electrons. And you'll notice it's all the way at the end of the p. So it has 6p electrons. You can just count the blocks up and you'll see you have 6p electrons. Argon is inert. It's a noble gas. It does not react because it doesn't have to. It has a full octet. Notice that, and this is something that has always confused me. I was telling my friend Kim this the other day. I really hope that when I pass, that God will give me the opportunity to ask at least one question before pressing that button and sending me down the direction I really should have gone in the first place. And if I'm allowed to ask one question, my question is going to simply be, why P? The most stable electronic configurations, the noble gases, they don't react because they're stable electronic configurations. That's why elements are trying to get to some noble gas electronic configuration. But the most stable electronic configuration is not a full valence shell, because argon has empty d orbitals that it's not going to use. The third shell has d orbitals. Argon has those d orbitals. It just doesn't use them. Well, turns out argon, there are some compounds you can make from argon, and in order to do that, they do kind of use those d orbitals. It's the only way you can do it. But it only forms them under extreme conditions. It does not like forming compounds. So it has those d orbitals, but this the stability. It's stable because it has a filled p subshell. And this is where the octet rule comes from. We have one s orbital, and we have 3 p orbitals. This gives us a total of 4 orbitals. And as you recall, each orbital can hold up to 2 electrons. 4 times 2 gives us 8. This is why we have the octet rule. That's where the octet rule comes from, trying to fill both the s and the p orbitals. So if we look at chlorine, chlorine's electronic configuration is very much like argon. That's why I chose it. It's actually right next to argon. Again, it has a filled s subshell, but it only has 5 p electrons. Just count the blocks over, and you have 5 p electrons. Don't worry about learning this particular, this is just a graphical representation. But notice this is why chlorine is so reactive. Because it's so close to the to the argon electronic configuration. It's just 1 electron away. It's also a free radical. Makes it extremely reactive. That's why all the halogens are so reactive. Chlorine is used as a disinfectant. Sometimes chlorine gas is actually added to drinking water to kill off microbes, bacteria, what have you. Sometimes it's added in the form of bleach. They will put bleach in water, always at very low concentrations. It's mostly gone by the time it reaches your tap. But bleach basically decomposes to form chlorine gas. So bleach, which is actually a salt, sodium hypochlorite, when it decomposes, it forms chlorine gas. So when they add it, it's almost like adding solid chlorine because it's not going to stay sodium hypochlorite very long. This is also why sometimes if you're in a city, you can taste that weird chlorine taste. It's the same chlorine that's added to swimming pools. Again, very low concentration. Kill off anything in swimming pools so people don't get sick. And that chlorine smell, sometimes you can get it from your tap water. And that just means that at the processing plant, they have the chlorine concentration too high. I used to actually work as a chemist that worked with these people. And it just means they have to add less chlorine or less bleach, whatever it is, because that chlorine should not be reaching your tap. But sometimes it does, if their balance is a little bit off. But here's a Lewis dot structure. We're going to draw the Lewis dot structure for chlorine. Start with the element symbol. Now, actually, before we draw the Lewis dot structure, I'm going to put it off to the left here a little bit, give myself a little more room. There are 4 regions around the chlorine symbol. You have the top and the bottom. You have the left and the right. I told you once before, I told you this. I told you this. An orbital is nothing but a region of space where we are most likely to find the electrons. That's all it is. A region of space of high electron density is really what it is. Now, keep in mind, a Lewis dot structure is not intended to reflect the way these things actually look. It's a cartoon. It's a cartoon version of electronic configuration, but it helps you to visualize what's happening. So what we're going to do is we're going to forget the s and the p orbitals. We're going to combine them into these four regions, which actually mathematically is what happens in compounds. The s and the p orbitals do what we call a hybridization. They actually combine to form four hybridized orbitals, which is going to become important a little later in the chapter when we talk about shapes of molecules. Everyone seems to know that water is a bent molecule. By the end of this chapter, you're going to understand why it's bent, why it has the shape that it has. Kind of a cool story, actually. So what we're going to do in each one of those four regions, we're going to put a dot, just a dot, to represent one of these to represent an electron. One dot per electron. So if you look at chlorine, we have 7 electrons. By convention, it does not matter where you start. You can start at the top, the bottom, the left, the right, doesn't matter. Usually I start at the left just out of practice, just out of habit. Today I'm going to start, I don't know, let's start from the left. Just do something a little different because you can't do anything wrong. It's just a cartoon. But, and this is a big hairy but, as you add electrons, as you add those dots, 1 dot per region first until you put 4 dots around it, then start pairing the dots. So I'm going to start here. 1, 2, 3, 4. Now each region has 1 electron. And remember, these regions represent orbitals. So now we have 4 electrons and 4 orbitals. We still need to add 3 more. Doesn't matter where you add them, but pair them up. Like this. Now you don't need to draw these little circles when doing a Lewis dot structure. So the correct Lewis dot structure might look something like this. So this is the actual Lewis dot structure. Now, like I say, that unpaired electron doesn't matter where you put it. In fact, it's going to be easier when we do more complex Lewis dot structures to kind of be able to move that unpaired electron around. So it doesn't matter where you put the unpaired electron. Maybe in your notes you put it on the top or on the bottom. I don't know. Wherever you put it, it's fine. These represent the valence shell electron. The valence shell electrons. And this is also why Lewis dot structures are kind of limited. Typically, you do not do Lewis dot structures for transition metals. And for things like chlorine, well, okay, we'll do something else. Usually you ignore the transition metal electrons, you ignore the d and the f orbitals altogether anytime you do Lewis dot structures. Just ignore them. That's because we're working really with that old octet rule. So there's special names for these. Anytime you have a pair of electrons, these are called non-bonding electrons. Or, and you'll hear me use this term frequently, lone pair electrons. Those are called lone pair electrons. They are lone pair electrons because they're happy. You can only put 2 electrons in an orbital, never more. And don't try to use these lone pair electrons for bonds. They are not bonding electrons. They do not bond. Sometimes they do, but when that happens, that's kind of beyond the scope of this course, I believe. I don't think we're going to talk about that. But if you have those empty d orbitals, you can kind of force them apart. But again, it's under extreme circumstances and it's beyond the scope of our course. So we're not going to worry too much about that. So just consider these lone pair electrons as non-bonding. They just don't participate. They're happy. They're going to sit around and watch what happens, but they are not going to participate. Unpaired electrons are bonding electrons. They are bonding electrons. Those are the electrons that participate in chemical bonding with other elements. So anytime you have an unpaired electron, those are the electrons. Those are the electrons that participate in bonding. So if you look at your periodic chart, the one that I have with the Lewis dot structures is actually missing the noble gas column. So it's going to look a little strange. If you look at a normal periodic chart, how do you do this? Actually, let's go to one of those. So let's figure out the Lewis dot structure. Yeah, it's fine. For oxygen. Clear my periodic chart. We don't need that scribbling. So oxygen is here. Let's do the Lewis dot structure for oxygen. All we have to know is the number of electrons in the valence shell. So just count them up. 1, 2, 3, 4, 5, 6. There are 6 valence shell electrons in oxygen. So now we go back to our Lewis dot structure. With that in mind, all we have to do is put 6 electrons around our oxygen. 1, 2, 3, 4, 5, 6. That's the Lewis dot structure for oxygen. Let's do one more example because I want to demonstrate this as well. Let's do the electronic configuration for let's say selenium, element number 34. And by the way, this also, the oxygen shows why oxygen tends to be -2, because it has 2 bonding electrons. That means unpaired electrons, and electrons don't like being alone. So it's going to pick up 2 electrons from somewhere. Lewis dot structures kind of help us to see this. Now, normally, you don't do Lewis dot structures for ionic compounds. Usually it's for only covalent compounds, and we'll talk about covalent compounds in a bit. Actually, a little bit. Can we talk about it in this chapter? We're going to talk about it, but anyway. So let's go back to our periodic chart. And we see selenium over here. Okay. All we have to know is how many, and it's not even true. It is not true to say how many valence shell electrons, because notice that selenium has all those d electrons in there. The reality is for Lewis dot structures, we're only looking specifically at S and P orbital electrons, valence shell, only S and P valence shell electrons. So for selenium, we have 1, 2, always count the S electrons, it's S and P. We're going to skip all of these. We're going to skip the transition metals. 3, 4, 5, 6. So selenium also has 6 electrons, S and P electrons in its valence shell. So selenium is going to look very similar to oxygen. We're going to put 6 electrons around selenium. Just like that. Is that fair? Doesn't look very similar, does it? I mean, the unpaired electrons are in a very different locations. Well, one is in the same location, the other one is not. These Lewis dot structures are cartoons. All they are, just cartoons. So it does not matter where you put those unpaired electrons. The same information is being relayed in both of these Lewis dot structures. Both of these Lewis dot structures are telling us that we have 2 sets of lone pair electrons. We have 2 sets of lone pair electrons and 2 bonding electrons. In both of these, even though the location changes, they both have 2 lone pairs and they have 2 bonding electrons. Before we move on, are there any questions about this? Okay. Hearing nothing, I'm assuming we are good. So let's move on. There are 2 ways to fulfill an octet. Oops, wrong way. The electrons can transfer. The example we did earlier in the course of sodium chloride, sodium desperately wants to lose 1 electron. So it just gives it up. It becomes a +1 charge. Chlorine really only wants to gain 1 electron. So it picks it up. It forms a -1 charge. That electron is physically transferred from one element to another. In a compound, what is holding sodium chloride together is simply the charges of the ions. Chlorine becomes negatively charged, sodium becomes positively charged. The ionic compound is just held together by attraction. If you go to a party with somebody that you're attracted to, your spouse or whoever it is, if you go to a party with them, are you with them the entire time? No. Our only class participant today is Kim. She's female, so I'm going to use the female example. And when they go to a party, Kim is not going to stay with her. Actually, she's married. She's not going to stay with her husband the entire time at the party. She's going to go off and talk to her friends. He's going to go off and talk to his friends. They're there as a couple. They are there together, but they're not together. This is called dissociation. They're free to go and see whoever they want. They absolutely must go and see whoever. Well, they don't have to. So they're at the party together, but they're not tied together there, you know, it's the way it is. The other thing we can do is we can share electrons. This is called covalent bonding. When electrons are shared, it is called covalent bonding. So for example, we can have our oxygen probably one of the best known examples of a covalent compound is water. Water has 2 parts hydrogen to 1 part oxygen. Now, hydrogen, if you look on the if you look at the periodic chart, you will see that water has only 1 electron. I'm sorry, hydrogen has only 1 electron. So we can share these 2 electrons. Because there are 2 electrons in that orbital with oxygen, we count it as 2 electrons. We're going to talk about this a little bit later. It's H2O. Notice that if we just put 1 hydrogen, now this electron is no longer a free radical. That electron is being shared. So it's paired. It has 2. But we still have a second electron that is unhappy. That electron is still unpaired. That's why it requires 2 hydrogens for each oxygen. Don't draw this in your notes. Do not draw this. There you go. Now we can take, going to be ugly. Compare, I don't want to go right through the hydrogen. We can do it this way. Isn't that ugly? Let's not do that. That's ugly. Remember what I told you. Lewis dot structures, now you can start writing in your notes. Lewis dot structures are cartoons. It does not matter where we put that unpaired electron. So why not put it next to this unpaired electron? Now we can form a bond here, which looks much prettier than trying to wrap it around that element symbol. Now, all of those electrons are happy. Hydrogen is always an exception to the octet rule because it only wants 2 electrons. And now we know why. Hydrogen only has the 1s subshell. There are no p subshells. So it can only take 2 electrons. When you draw a Lewis dot structure, we're going to come back to this and do we're going to do more examples. I'm just kind of showing this to you as an introduction. This is a Lewis dot structure of a compound. To check the octet rule, anytime you have shared electrons, those count towards the octet rule. So hydrogen is happy. It wants 2 electrons in its valence shell. It has 2 electrons in its valence shell. Oxygen has 2, 4, 6, 8 electrons. So oxygen now fulfills its octet rule. It has shared electrons, and now there are 8 electrons around the oxygen, even though 2 of them are shared. It now has 8 electrons. This is a valid Lewis dot structure, and we're going to do more complex examples soon. But how do you know if it's going to form an ionic or covalent compound? We know by using the Pauling electronegativity scale. Linus Pauling was brilliant. He died in the 90s, and he was in his 90s when he died. He was almost 100. And the year that he died, he had a single author paper which is just unheard of in this day and age. But he did it. Electronegativity scale. And we're going to talk about that after the break. Let's come back at 10:45, please. And I'm going to stop sharing, and I'm going to pause recording. And we are recording. So if you open your book to that, wherever page it's on, your Pauling electronegativity scale, the second period is really the easiest to memorize. I'm not going to ask you to memorize any of it, honestly. But starting at lithium is 1, and it goes up 0.5 for each one. So it's 1, 1.5, 2, 2.5, 3, 3.5. Here's the way it works. Notice that hydrogen. Electronegativity is a measure of the desire an element has for an electron. The stronger an element's attraction is to an electron, the higher the electronegativity. That's all it is. It represents how attractive an element is to an electron. The numbers, the raw numbers themselves, are not going to mean much to you. Hydrogen, for example, is 2.1. Oxygen is 3.0. Sodium, we're going to look at two compounds here. Sodium is 0.9. Oxygen, well, sorry, I didn't want oxygen. Chlorine is 3.0. Electronegativity is often represented with this funny little epsilon, which I'm not sharing my screen. And you're just laughing, waiting how long it takes me to recognize that.
I was going to tell you in a minute or two.
Okay. So oxygen has this funny little epsilon. This is the Greek letter epsilon. That's what we use to represent epsilon. And remember, delta always means change in. It's a mathematical symbol. You're going to see it a lot. So what we're looking at is the change in electronegativity. Always look at the absolute. Always look at the positive change in electronegativity. So for sodium chloride, notice that chlorine has the larger electronegativity, so I'm going to put that down first. The change in electronegativity, which we know is an ionic compound, is 2.1. For water, and notice we only do it for one bond. This only works per bond. So even though the formula for water is H2O, we're going to look at the hydrogen-oxygen bond. Just one of those bonds, not both of them, because they're both going to be the same, honestly. Do it for one, you do it for both. Notice that the difference in electronegativity for the ionic compound, sodium chloride, is much higher than the difference in electronegativity for water, for hydrogen, oxygen. But it's still a fairly strong bond here. A fairly big electronegativity difference for hydrogen and oxygen. Okay. We'll talk about that in a minute. If the difference in electronegativity is high, then you have an ionic compound. If it's low, let's look at oxygen. Now, oxygen is a double bond. We're going to talk about that a little later. Come on. The difference in electronegativity, of course, is zero. We would expect that because it's the same element. One oxygen does not have a stronger pull for electrons than the other element. So the change in difference in electronegativity is zero. A very high difference in electronegativity is ionic. A very high difference in electronegativity is an ionic bond. A low difference in electronegativity is covalent. Now, both of these are covalent, but there is a difference. There is a difference. Notice that in the hydrogen-oxygen bond, the electrons are shared, but the oxygen has a much stronger attraction for those shared electrons than the hydrogen. So they're not shared equally. They're not shared equitably. They're shared. Did you ever try to give just one toy to two kids? Here, this is for you to share. Yeah, my butt. What ends up happening? Okay, technically it's shared. Who gets it most of the time? My sister. Because she was stronger than I was. So of course she gets the toy most of the time. If it was something we both wanted, she won. If she was ignoring the toy, I could sneak it sometimes and play with it for a little bit until she realized I was playing with it, and then she comes, that's my toy, and she'd take it away from me. It's supposed to be shared. Yes, I was a little whiner. So the electrons are shared, but they're not shared evenly. They're going to spend more time around the oxygen than the hydrogen. This is called a polar covalent bond. It is somewhere between ionic and covalent. It's covalent, but it's not equitable. So this is a polar covalent bond. This is a non-polar covalent. All right. We're going to talk about molecular polarity a little bit later in this chapter. And this is what we're talking about. What's the charge of an electron? Negative. Thank you for participating.
You're welcome.
If we physically transfer the electron, the element that loses the electron has a full positive charge. The element that gains the electron has a full negative charge. They are ions. They are electrolytes. That's what an electrolyte is. It's an ionic compound that's dissolved in water. Electrolytes are just like regular electrodes, but they have 1/3 fewer calories. That was like a joke. It's just smaller. An electrolyte is kind of an interesting thing. We're going to get back to polar covalent in a moment here, but I want to explain why we call them electrolytes. Covalent compounds are not electrolytes. Ionic compounds are. If you are standing in a salt mine, nice dry salt mine, and you drop a high power line, a high power cable falls down into the salt, are you in trouble? No. Salt does not conduct electricity. If you are standing in highly distilled water and a power line falls into the puddle, are you in trouble?
Yeah.
No.
No.
As it turns out, water does not conduct electricity. What does conduct electricity are electrolytes in the water. That's why you have to be careful of power lines that have fallen, because even if that water was very pure, as soon as you dip your grubby little toe into it, it's not pure anymore. Those ions, ionic compounds, can dissociate. We already talked about that. So the sodium goes off, the chlorine goes off. They're together, but they're not together. They're ions in the water. Those ions, those dissociated ions in the water, that's what conducts electricity. That's why it's called electrolytes. Even at very, very low concentrations, those electrolytes will conduct electricity. So believe me, if you're standing in a puddle outside, it's not pure water. And that puddle will conduct electricity because it has water and dissolved electrolytes. Little bit of trivia for you this morning. Yeah, it's still morning. So anyway, these electrons are not being shared equally, but the electron is negatively charged. It's not transferred, so we don't have a negatively charged oxygen, and we don't have a positively charged hydrogen. They're close enough. These two children are close enough in strength that even the weak one has a chance at playing with that toy. But it's uneven. So we don't have a full negative charge, but near the oxygen, because the electrons are spending more time around the oxygen, we're going to have not a full charge. We're going to have a kind of a part of a charge, kind of a little bit of a charge. We're going to have a partial charge. The oxygen will be partially negative, which we denote like this. That little symbol there is lowercase delta. A lot of people are not aware the Greek alphabet has upper and lower cases. We're so used to seeing the triangle and we say, oh, that's delta. That's technically uppercase delta. Uppercase delta. This is lowercase delta. It's a partial negative charge, not because the electron's been transferred, but because it's being shared unevenly. In the world, and I've said this before, and you're going to hear me say it a lot, the world is electrically neutral. The world is electrically neutral. So if there's a partial negative charge on the oxygen, what has to be on the hydrogen? A partial positive charge. That unshared electron, remember those two electrons in that bond, and here's something else for you. A covalent bond is always two electrons. Covalent bonds, without exception, are always two electrons, no more, no less. A covalent bond is always two electrons, one from each element. So this bond, one of those electrons in this bond came from the hydrogen. And now it's spending more time with the oxygen than the hydrogen. So the hydrogen is partial positive. We say that this is a polar bond. And we denote polar bonds with this symbol. This means the same thing as this lowercase deltas. Basically means the same thing as the lowercase deltas. That arrow tells us that this is a polar bond. And it tells us that the hydrogen is where the plus symbol is. The hydrogen is the partial positive, and we put the plus side of this arrow towards the partial positive. It points in the direction of where the electrons are spending most of their time. So it always points to the partial negative side. So the partial negative is here where the arrow ends. Okay? So really three kinds of bonds. Ionic, polar covalent, non-polar covalent. All right, you with me? The question is, how do we know what's what? Well, we know if it's polar covalent or non-polar covalent or ionic based on Pauling's electronegativity scale. You just take the difference, just like we did up here. You just subtract the two. But we need some kind of a cutoff. We need some kind of a cutoff of what goes where. These cutoffs vary a little bit. Depending on the author. So if the difference in electronegativity is less than 0.5, it is non-polar covalent. If it is less than 0.5, it is non-polar covalent. If the change in electronegativity is between 0.5 and 1.5, if I'm remembering correctly, it is polar covalent. Polar covalent. And if it is greater than 1.5, than it is ionic. I'm looking to see if I can find the scale in my textbook, and I'm really not finding it. So I'm not sure if it's 1.5 or 1.2. I'm really not sure if it's 1.5 or 1.2. So if the textbook says, if your textbook says something other than the scale, go with your textbook. All right. Go with your textbook. Any questions so far?
No.
I think we're going to do some nomenclature now, but there's another weird thing. Well, let's do simple nomenclature first. Yeah, nomenclature. So let's go back and review. We did this, I think, on the first or second day. Let's look at this compound. Now, normally, and we talked about the charges of different families. In column 3A, the aluminium is the only element whose charge we should remember. It's the one that has a very common charge. Do you happen to remember what that charge is? Actually, at this point, it's pretty easy to figure out how many electrons in the valence shell.
3.
3. So it must be going to lose all 3 electrons. Aluminium is always +3. Oxygen is always what? Correct, -2. How do we figure out the formula for aluminium? Well, okay, I just said it, but how are we going to figure out the formula? Drop the chart, the signs, and just do your crossover trick. And there we go. Now, anytime you do this cross trick, you must always remember to check for common denominators. There's no common denominator between 2 and 3. So this is the correct formula. We can check to be sure we did it correctly, put those charges back. I always like to put them in parentheses so I don't get confused. Multiply them. 3 times 2 is +6. 3 times -2 is -6. Compounds are always electrically neutral. Valid compounds are always electrically neutral. So those charges should add up to 0. If they don't, you did something wrong. To name this, you always start with the name of the cation first. Aluminum, or if you're British, aluminium. Then put the name of the anion, but change the ending to IDE for simple ions. Okay. When I say simple ions, I mean ions that just come right off the periodic chart. It's just oxygen. So it's oxygen, change the ending to IDE, aluminium oxide. Okay, we've done that before. That's just a review. In fact, I may have even used the exact same example. Here are two well-known iron compounds. Using our simple nomenclature device, and I want you to notice as I'm writing this, I'm leaving a space between the iron and the chloride. You name the cation first, iron, followed by the anion with the ending chlorine changed to IDE, chloride. So what's the name of the compound on the right? Iron chloride. Do we see a problem here? What's the problem?
They don't match totally.
It's the same name. If I wanted to order iron chloride, which one would I get? These are both real compounds. They're both valid compounds. Which one would I get?
I don't know. One's 2, one's 3.
Exactly. Now, how do we distinguish these? Now, there was a time, and I hated this. The old convention was you change the ending of the cation. So the one on the left would have been ferrous chloride. The one on the right would have been ferric chloride. And you just had to remember which one has, well, actually, in the ending talks about the oxidation state. When you hear me say oxidation state, that just means charge. That's just the charge. If we look up iron on the periodic chart, we see that it is actually, it's kind of interesting. Iron is the most stable nucleus on the entire periodic chart. Anyway, it's element number 26. It is in the transition metals, and that's why it has more than one possible oxidation state. Now, with aluminum oxide, we don't worry about the oxidation state. There's only one known oxidation state for compounds, including aluminum, and that's always +3. So we just say it's aluminum oxide. Everyone understands it's +3 oxidation state. But we have to be able to distinguish between these two irons, and I don't like memorizing endings. I don't like us and ick, and then all of a sudden you start getting into hypo-ick or hyper-ick or hypus or God, who knows? It's terrible, terrible, terrible convention. Here's what you do. In order to name these, first you need to figure out the charge of the cation. That's really what's changing here. The oxidation state or the charge of the cation is what's changing. So let's figure that out. We know that chlorine is always, always, always -1. So -1 times 2 gives us a -2 charge from the chlorine. -1 times 3 gives us a -3 charge from the chlorine. Compounds are always electrically neutral. So the charge of the cation must cancel the charge of the anion. So what's on the left compound? What is the charge of the iron? Has to be what?
2.
+2. Very good. And on the left, must be +3.
Oh, 3.
Yeah. Has to cancel that -3 charge. Each chlorine is -1, but there are 3 of them, -3 charge. Therefore, the iron must be +3.
Okay.
Here's how we do this. With the exception of those families and aluminum, where I told you what the charge is always going to be, we always have to include the oxidation state of the cation. We always have to include the charge of the cation. We do that using Roman numerals in parentheses. So on the left, we have iron 2 chloride. And on the right, we have iron 3 chloride. Okay. Would you like to see another example?
Sure.
Let's do another example. Let's do one the opposite direction. Chromium 4 sulfide. Now, if they give you the Roman numerals in parentheses, that's even easier because you don't have to memorize those. It's given to you. If it's Roman numeral 4, the charge of the chromium is
4.
+4. Sulfur is a chalcogen. It is right under oxygen. What do you suppose the charge of sulfur is?
The same as oxygen.
Which is
3.
-2.
-2. Okay.
Yeah, oxygen, if you look at it, actually, let's look at sulfur since we're on this one. So sulfur, notice it has to gain 2 electrons to get a noble gas or argon electronic configuration. So if you look at the periodic chart, just count over to the noble gases. It is 2 columns away, -2 charge. Okay, so the anions are actually pretty simple. Now we do our usual cross trick. And we get Cr2S4. Is that correct?
No.
Because has a common
Denominator.
As a common denominator. You must take that common denominator out. Crs2. Crs2. We are about a minute out from the end of today. We did not quite get as far as I had hoped, but we did pretty well. We're going to talk about something called polyatomic ions next week. Sort of a combination of both ionic and covalent bonding. But for today, we're pretty much going to call it. Do you have any questions about chemical bonding, Lewis dot structures, polarity?
No.
Okay, hearing no questions, I will let you go. Don't be late for your next class. Thank you for your attendance.